Canada is one of the most spectacular countries in the world. Nature at its most beautiful. However, only a very small part of the country is actually inhabited, so a lot of places are remote, difficult to access, and far away from any assistance or modern technology. But things still need to run on time. In the middle of nowhere, train tracks sometimes need to be repaired. Engineers have to use their ingenuity and one of the most impressive chemical reactions you'll ever see in a classroom. And it's one of my personal favorites, the thermite reaction. The temperature achieved is so high, one of the products is liquid iron, which is used to weld the train track back together. A bit extreme, but very efficient. So what chemical reaction can reach such power? And can we think of an even more powerful one? Let's raise the temperature. This is Think 4. The thermite reaction is an example of a highly exothermic displacement reaction. Iron 3 oxide will react with aluminium to produce aluminium oxide and the iron we were just talking about. In this reaction, aluminium will displace iron from its oxide. This is possible because aluminium is more reactive, meaning it will have a higher disposition to lose electrons and form ions, than iron, which is less reactive and will accept the electrons. This can be shown in an ion-electron equation. In the oxidation reaction, aluminium will lose 3 electrons and become aluminium ion, Al3+. And in the reduction reaction, the iron 3 ion, Fe3+, will gain electrons to form iron metal. Combining the two, which happens simultaneously, will display the overall reaction called redox reaction. So in this example, aluminium is pushing iron to reduce by making these 3 electrons available. We can then call aluminium the reducing agent, a substance that accepts electron. The other way, the iron 3 ion is allowing aluminium to oxidize by accepting these 3 electrons. We can then call iron an oxidizing agent, a substance that donates electrons. To identify which substance is the reducing agent and which one is the oxidizing agent, let's have a look at an example. Magnesium will displace silver from a silver nitrate. Magnesium metal will lose 2 electrons to become magnesium ion, Mg2+, and silver ion, Ag+, will gain 1 electron to become silver metal. The second ion-electron equation needs to be multiplied by 2 to balance the number of electrons to obtain the redox reaction. 2Ag plus Mg gives 2Ag plus Mg2+. The reason why an element will tend to lose or give electrons away is related to its electronegativity. We can predict that an element with high electronegativity, like the nonmetals, will tend to attract electrons and act as oxidizing agent. While on the other side of the periodic table, the alkali metals, for example, are very low on the Pauling scale and will act as reducing agents and form positively charged ions. Not only elements but compounds can be involved in redox reaction, as reducing or as oxidizing agent. The whole iron industry would not be possible without the strong reducing agent carbon monoxide. And examples can be seen across the entire electrochemical series. Some of these redox reactions can be extremely exothermic, like the thermite reactions, which we've seen can be used to produce molten iron in the remote parts of Canada. But there is even more. Why do you think I took the magnesium and silver nitrate example? This is definitely my favorite demonstration. Just a tiny spatula, smaller than a rice grain of both reactant in solid form are dying to react. A small drop of water to put the two together and boom, fireworks. This was Think 4. Thanks for watching.